Yeah, good afternoon, all the students. Now we'll start our fifth modules, continue our fifth modules first lecture. In yesterday's class, we haven't completed the topic. Yeah. In yesterday's class, we started understanding how to evaluate the hypothesis, right? When you are having when you have formulated some hypothesis and selected the best hypothesis based on its probability of it being consistent with the training examples, how do you evaluate whether that hypothesis that you framed with the sample also applies to the new data that is unseen by the machine learning model? How do you evaluate whether your hypothesis is generalizable? How do you evaluate that your hypothesis predicts in the same way that it has done with the sample, also with the larger population? How much is it generalizable? Is it giving the same accuracy, or it is giving a different lower accuracy or higher accuracy? That we are going to learn. For that, we have seen the motivation behind evaluating the hypothesis and the types of sample error and true error. Now, as I explained before, if you take a population P, now from that you draw a sample S. Okay, you take some part of this population, say 30% of the population you take as sample. Now, when you train the machine learning model by using this sample, you may find that it is performing with 95% accuracy, and 5% for 5% of the training, for 5% of the examples, it is predicting wrongly. In that case, we say the sample error with that particular sample is 5% here. Now, we have to evaluate our hypothesis in such a way that we need to identify whether it is performing with the same accuracy with some data point that is taken from the larger population. Because these data points outside the sample are not seen by the machine learning model. They are new data points or new instances to the machine learning model, because it is trained only on the sample. Okay, now any point you take outside the sample from the larger population and ask the machine learning model to predict, now among these 10 points, if it is predicting well with 9 points, and it is making a wrong prediction with respect to one data point, then we can say that it is predicting with 90% accuracy, right? This is called as the general populations or true accuracy, and 10% error that it is giving is called as true error. Okay, this is called as sample error, and this is called as true error. Did you understand now the difference between sample error and true error? Now, in order to understand, now what is the question that actually drove us towards evaluating the hypothesis? Given a hypothesis H and a data sample containing n examples, n training examples drawn at random according to the distribution D, what is the best accuracy of the hypothesis H over future instances drawn from the same distribution? As I told you, again, I'm explaining what is this distribution D. Distribution D is according to which particular pattern your data points are observed. As I told, they may be in the form of a normal distribution, or they may be in the form of a Poisson distribution, or it may be in a skewed type of distribution. Means most of the points lie in this range and very less points lie on the tails of this curve, right? That is called as normal distribution or Gaussian distribution. And in Poisson distribution, you take some polynomial term in order to explain the behavior of the distribution of data. right? Now we are just dealing for simplicity sake only with normal distributions. And you know that normal distribution is an inverted bell curve, right? Now we assume that the training examples that are taken are from a particular distribution D. Now, given a hypothesis H and a data sample containing n examples drawn at random according to the distribution D, here the distribution we assumed is D, what is the best estimate of the accuracy of H over future instances? You know the accuracy of H with sample instances, but what is the accuracy of H with unseen instances drawn from the same distribution? Again, here your assumption is even the new instances are also drawn from the same distribution D. Means they are also according to the normal distribution. Means they fall within a particular range. Most of the values fall within a particular range. Okay, then what is the accuracy of H over that kind of future instances drawn from the distribution, same distribution D? Okay, and one more question is, what is the problem error? What is the probable error in this accuracy estimate? Now, what would be the probable error associated with this accuracy estimate we are guessing? We are estimating. What is the accuracy that we are estimating? What is the probable error associated with it? Okay, these two questions we are interested in. That is why we try to evaluate the hypothesis. Now, to answer these questions, we need to distinguish carefully between two notions of accuracy or equivalently error. What are those two notions? Sample error and true error. Sample error is the error rate of the hypothesis over the sample of data that is available, that is taken for training the machine learning model. And what is true error? It is the error rate of the hypothesis over the entire unknown distribution D of examples. It is drawn from the part where the machine learning model hasn't seen. Means it is drawn out of the sample, which is actually used to train the machine learning model. We use one sample to train the machine learning model, right? Now a new instance is drawn outside this sample. Now what is the error associated when this new instance is predicted by the machine learning model? That is called as the true error. Okay, so this error associated with the sample is called sample error, and after predictions made with these data points, if any error is associated with it, that is called as the true error, because that is the actual estimation, right? Say my students are performing very well in the classroom. Now I send them to competitive exams, and if they perform well there also, then my training is proper, right? So when I see that 5% of my students in the classroom are not performing well, that is called the sample error. Now I send you to some competitive exam, and there I try to guess the performance of various other students based on the knowledge I gained from your performance. Now any error associated with that larger population, that is called as the true error. So my estimation is becoming wrong if the true error is very high. Means my sample, if the difference between my sample error and the true error is too much, then I haven't studied well about the student population. My experiment is biased only to my class students. Got it what I'm trying to tell? I have performed an experiment about students only with respect to my class. Now I found that 5% of the students only are not performing well. That is my sample error. Consider. Now I have sent them to perform with compete with other students. Now I have taken overall students data and I'm trying to estimate their performance. Now there lot of error is associated. True error is very large compared to the sample error. Means 30% of the students are not performing well compared to my classroom sample error 5%. It indicates that My model is not generalizable. I did not make the experiment properly. My experiment is biased to only a single classroom of students. That is why the machine learning model is giving, though it is giving less error with respect to the sample, it is giving high error with respect to larger population. Right? In that case, I say my model is not generalizable. I have to reduce the error, I have to reduce the difference between this sample error and true error. My sample error, if it is same as the true error, then my model is generalizable. Then my model is performing very well. Then the accuracy of my machine learning model is very high and it is not showing any overfitting symptoms. Okay. This is the difference between sample error and true error. Now, the sample error of a hypothesis with respect to some sample S of instances drawn from X, when I'm reading this, you should be able to understand, right? Some instances drawn from X means X is set of all training examples. Say all students' data. Now, from that, you're drawing only sample. Sample means say some 30 students' data or 40 students' data. Like that. That is called as sample. Okay. When you have 100 in the population, 100 data points in the population, you pick only 30 data points from that. I say I'm doing 30% sampling here. Okay. So the sample error of a hypothesis with respect to some sample S of instances drawn from X is the fraction of S that it misclassifies. For that, we define the sample error as the number of errors it has made, that is the difference between the target function and the label predicted by the hypothesis, indicated by delta f of x, h of x. Okay, count those errors and find the average. That will be your sample error. Say it is making 5 wrong predictions out of 100 data points and 95 correct predictions. In that case, we say the sample error as 0.05, or in percentages we can say 5% sample error. Normally the error lies between 0 and 1. That is why I am trying to write as 0.05. Okay. Both are same representations. 5 divided by 100, you can represent it as 0.05. But if you want to know the percentage of error, it is 5% error. Right? That is why we have given here delta f of x, h of x is 1 if the target label is not equal to the predicted label. If there is an error, there is no matching in the predictions, or 0 otherwise, means if there is matching in the predictions, then there is no error. Error is equal to 0. That is what we mean by this representation. Sample error is the average of all the errors made. Right? No, sorry. Rather than average, we should tell as ratio of the errors made. Means how many number of errors are made by total number of predictions made, or by total number of examples that are given, training examples that are given. So that is 0.05. That is called the sample error. Now, what is the true error? True error of hypothesis H with respect to target function F and distribution D is the probability that H will misclassify an instance drawn at random according to D. Okay. Again, I told you this in the previous class. You're drawing at random from a distribution D. You're not drawing from some outlier, the data point from some outlier. Outlier is not according to a normal distribution. It lies somewhere in an extreme point. Okay, so you're drawing an instance at random according to the distribution D. In such case, how do you represent the true error? It is the probability of the target label being not equal to the predicted label, h of x. Here the notation probability of x belongs to D denotes that the probability is taken over the instance, total number of instances under the distribution D. Okay, so what is the probability of an error in the prediction. That is your true error. This thing, how I can read simply, what is the probability of error in the prediction? That probability is called true error. If it is high, the true error is very high, indicating your model is not generalizable. If the probability of this error in the prediction is low, true error is low, indicating that your model is highly generalizable, highly acceptable, because it is giving lesser true error, which is almost similar to sample error. When the sample error and the true error are matching, then your machine learning model is the ideal machine learning model. Now, what we usually wish to know is the true error of the hypothesis, because this is the error we can expect when applying the hypothesis to future examples, right? It is not the error it is not the error that we encounter or we face when we are training the machine learning model, that we are not interested in. When that model is applied to unseen data, how it is performing, that is really of interest, and that is called as the true error. Now, all we can measure, however, is the sample error only. Can we measure the true error properly? It is not at all possible. Now, you take a sample, find out its error, and take another sample, find the error. These two may not be matching. Why? Because sample is random pick from the population. And remember, always approximation is associated with the sample what we pick. You try to approximate, you don't try to exactly predict what is the error associated with that sample. You are just approximating it, you are just guessing it, you are just estimating it. Okay, all we can measure here is the sample error. So you can measure the sample error for that particular sample of the hypothesis for the data sample S that we happen to have in hand. Okay, that is only under our control. Measuring the true error is not under our control, because this sample is giving very good estimate and it is matching with the true error, but another sample is giving very low estimate which is not matching with the true error. That is why we have only sample measurement, sample error measurement under our control. Now, what is the main question? How good an estimate of true error is provided by the sample error? Now you know about the sample errors. Now can you use that sample error to give a better estimate of the true error? That is the main question. For that, we need to consider confidence intervals for confidence intervals. Okay. Now here we are going to cover confidence intervals for discrete valued hypothesis. Discrete valued hypothesis means you have 95% or 96% or 97%. You don't have 95.1, 95.2 like that. Okay. You're just considering the discrete values. Suppose we wish to estimate the true error for some discrete valued hypothesis H based on its observed sample error over a sample S. Okay, now how do you understand this problem? The sample S contains, assume n examples. N examples means n data points. Say 30 students' data drawn independent of one another. Means one data point that is drawn doesn't have any effect on drawing the other data point. Okay, that is called as drawn independent of one another and independent of H also. Consider you don't have any knowledge about the statement made about the student group. It is independent of H. Now, according to the probability distribution, D it is drawn. Now, N let it be greater than or equal to 30. Means the sample points or the data points, let it be greater than or equal to 30 points. Means 30 students data, more than 30 students data. Now hypothesis H, assume that hypothesis H commits R errors over these N training examples. Now how do you calculate the sample error? Number of errors made are divided by the total number of data points N. That will give you the sample error. Very easy, right? It is ratio of the errors that is made. And how do you calculate that? Number of errors made by the total number of data points. Means out of n data points, how many labels are predicted wrongly? That is the error made. And here we are considering that as R. R number of errors are made out of n data points. R predictions are made wrong out of n data points. Got it? Now, under these conditions, statistical theory allows us to make the following assertions. What is the difference between assumption and assertion? Assumption means we are making some, we are taking some things as granted. We are assuming that these are true. And we start our experiment. Now we get some confidence after that experiment to assert something, to state something, okay, to tell something with some confidence. Those are called as assertions. Now, under these conditions, statistical theory allows us to make the following assertions. What assertions? Given no other information, consider that there is no information given. Assume that there is no information given. The most probable value of true error is equal to sample error. That is, most of the times will be optimistic, right? We always think that, we always assume, try to assume that our machine learning model, which is giving this much accuracy, is performing with the same accuracy when it is applied in the real time. That is, true error and the sample error are equal, almost same. If they are not equal, almost same. The difference between the sample error and true error will be as minimum as possible. That is what we assert when no further information is given. Now, with approximately 95% probability, understand this carefully. I'm going to talk about some mathematical terms here. Understand this carefully. With approximately, wake up students, if anybody is sleeping, with approximately 95% probability, the true error lies in the interval defined by this equation. I'll show you. I'll calculate and show you how it lies between this, in this particular interval. What is the interval? How is it defined as? Sample error plus or minus 1.96 multiplied by square root of sample error multiplied by 1 minus sample error divided by n, the total number of data points. Okay. You will understand how we have used this more clearly as I proceed with the explanation. Now, to illustrate this particular representation, suppose the data sample S contains n equal to 40 data points or 40 examples, training examples, and that hypothesis H commits 12 errors over this data. Now, tell me, what is the sample error? 12 errors are committed out of 40 data points. So what would be the sample error? 12 divided by 40, and that is 0.30. In percentage, it is 30%. Okay, because errors we normally represent between 0 and 1, we are writing it as 0.30. Now, given no further information, the best estimate of the true error is the observed sample error 0.30. Okay, no further information is given. In that case, what is your assumption? You assume that according to statistical theory, you assert that your sample error is equal to the true error. Means your sample error here is 0.30. Even your true error also would be 0.30. I say would be. I'm not still saying it will be. Okay, would be 0.30. But we do not expect this to be a perfect estimate of the true error. Again, we are asserting that according to statistical theory. But is it the real case? We do not expect this to be a perfect estimate of the true error. Means error D of H. Though we assert according to statistical theory that sample error would be equal to true error, that is not the perfect estimate of the true error. If we were to collect a second sample now, let us see why it would not be a perfect estimate of the true error. Let us see. If we were to collect a second sample S dash, initial sample is S. Now we are collecting a second sample S dash, again consisting of 40 different samples. These 40 samples are not at all there in this sample now. This is again entirely new sample S dash that is taken, containing 40 new randomly drawn examples. We might expect the sample error S dash H to vary slightly from the sample error S. Now the sample error of S dash would be slightly different from sample error S. Remember, none of the data points are dependent on each other. They are not picked depending on each other. They are randomly picked. They are independently drawn. Okay, so there will be some difference in the error associated with sample S and sample S dash. Now we expect a difference due to random differences in the makeup of S and S dash. This is what I said. All the data points are independently drawn, randomly drawn. They doesn't have effect on the other draw. That is why there is a difference between S and S dash errors. Now, in fact, if we repeated this experiment over and over again and again, each time drawing a new sample S containing 40 new examples each time, S, S dash, S double dash, S triple dash, you keep on drawing various samples with different data points, each of them having 40 data points. I'm telling 40 is the number of data points, but the data points, the samples are different. Okay, we would find that for approximately 95% of these experiments, the calculated interval would contain the true error. What do we mean by this? If you repeat this experiment again and again for different samples, in that case, 95% of these experiments, the calculated interval would contain the true error. Means this true error would be as much similar as to sample error. We are believing, we are confidently saying that 95% of the time true error would be equal to sample error, almost equal to sample error. Only 5% of the time it may vary. Okay, that is why we call this 95% as the confidence interval. We are telling that our machine learning model trained on a particular sample S will perform 95% of the time correctly with the new data instances. Got it? Now for this reason, we call this interval 95% as the confidence interval estimate for the true error. This is the confidence interval estimate for the true error. 95% of the time we are stating that true error will be equal to sample error. Means 95% of the time your machine learning model will predict well. Its performance with respect to sample error and the true error will be similar. Means it makes the same error with respect to the sample as well as the general population, unseen data, new instances. Okay. Now in the current example where R equal to 12 and N equal to 40, the 95% confidence interval is according to the expression what we have seen. According to this expression, how we are calculating? 0.30, the sample error. 12 by 40, the sample error is 12 by 40, the sample error is 0.30. Okay, so that sample error you have given. Plus or minus means it may be plus addition or plus or minus means you say this site may be 1 lakh cost, plus or minus 10,000 we say, right? Means we are adjusting the scale up to, it may be more by 10,000 or lesser by 10,000. Okay, so 0.30 plus or minus 1.96. This is the critical value. I'll tell you how critical value is calculated. Okay, just remember that this is the critical value Z. 1.96 minus, how is this 0.07 calculated? It is taken as square root of sample error 0.30 multiplied by, I'll write it here, it is more, I'll write in this part, focus here, square root of the sample error 0.30 multiplied by 1 minus sample error 0.7 divided by total number of sample points 40. So you will get 0.07 when you solve that. Okay, so it is Z minus 0.07. So that will give you 0.30, this first term, plus or minus, when you simplify this, you will get 0.14. Did you understand now how to calculate this one, the sample errors value? It is 0.30 plus or minus 0.14. Now this expression for the 95% confidence interval can be generalized to any desired confidence interval. Say we are telling 95%, we are taking 95% confidence interval in this case. Sometimes I may take only 80% confidence interval. Means what is that when I take as 80% confidence interval? I am stating that 80% there is probability of this true error. There is 80% of probability of this true error being similar to the sample error. Means 80% of the time I have confidence that my model performs well with the unseen data also, but 20% I don't have confidence. Means 20% it may give error, more error when compared to the sample error. True error will be very high, 20% of the time. But 80% of the time I am confident that my model gives same sample error as well as the true error. Means 80% of the time my machine learning model will perform well with the unseen data also. Did you understand now? That is called as my confidence interval. Here my confidence interval is 80%. When I say my confidence interval is 80%, Z value will change again. Critical value will change again. That critical value is available as a table, pre-built table for you. Okay, so whenever you are asked to calculate the critical value, whenever you are asked to calculate the sample error, you will be given the critical values for different confidence interval. Okay, so this expression for 95% confidence interval can be generalized to any desired confidence level. Now the constant 1.96, what we have used in case, and what we have used here is in case we desire 95% confidence interval. But if we want 80% confidence interval, or if we decide on 90% confidence interval, this critical value of Z will change. It will not remain constant for all the confidence interval. With each confidence interval, this Z value or the critical value will change. Now a different constant Zn is used to calculate n% confidence interval. Okay, did you see the association? A different constant Zn is used to calculate the n% confidence interval. So with 95% confidence interval, Z95 is what? 1.96. But for others, I'll show you the table. The general expression for approximate n% confidence intervals for error, true error is, now how you can calculate the true error? It is sample error plus or minus critical value multiplied by sample error into 1 minus sample error divided by n, square root over it. Okay, so that will give you the true error. So in this case, what is the true error? 0.30 plus or minus 0.14. So you're trying to tell the users to adjust for plus or minus 0.14 variation in the true error. Your sample error is 0.30 and the true error will be either 0.16 or it may be 0.44. 0.30 plus 0.14 is 0.44. It may be either 0.44 or it may be 0.16. It may be varying between this range, but it will not go out of this range. So you're guaranteeing the user that the true error associated with the machine learning model will be 0.30 plus or minus 0.14. Only this interval you're giving. Beyond that, it will not make any errors. That is what you're trying to assert. Right? Now you see these two figures, you will easily understand. Before that, let me show you the table. The constant Zn is chosen depending on the desired confidence level using the values of Zn given in the table. Say if you want to say that only 50% of the time your model will predict well with the unseen data, then the constant Z critical value will be 0.67. Now, if you say that your model performs only 90% of the time as good as with the sample, in that case, you take it as 1.4. Now, if you are very confident that 99% of the time your model will predict well with the unseen data, in that case, the critical value you have to take is 2.58. Now see this diagram, this first one. Observe the distribution. Now observe the central area. If you remove this part under the curve and this part under the curve, this green part is 80% of the area under the curve. Under the curve, if you take the total area as 100%, this green area will attribute to 80%. 80% of the confidence interval, and these are called as tails. On this tails, it is taken as 0.10 on this side and 0.10 on this side, and in the middle it is 0.80. Total it will become 1. Did you notice? 0.10 plus 0.80 plus 0.10. Total it is becoming 1. Okay, so under the area under this curve, it is showing that your confidence interval is 80%, means 80% of the time your machine learning model will generalize well, will predict well, even with the unseen data. Means your sample error and the true error will be same, almost same. You're asserting that. Okay, in that case, see, this part is 0.10 tail area, 0.10, and this part it is 0.10. These two are called as tail areas. In this case, Z is equal to 1.28. Z is taken from the table as 1.28 if it is 80% confidence interval. Now take in this case, area under the curve, you are taking the central area as 0.90, means you are telling that 90% of the time your machine learning model will predict correctly with the unseen data also. Means 90% of the time your sample error will be same as your true error. It will not make more errors than that. Okay, but 10% of the time there is a chance that true error may be higher or lower. Higher for this side, lower for this side. That is how the tail areas are taken as 0.05, 0.05. This side it is 0.05 and this side it is 0.05. In that case, what is the critical value? Z is equal to 1.645. That is what is taken here in the table. Got it? That is how the table is created to give to supply readily the Z values for different confidence intervals. Did you understand clearly now? Whenever you are going for data science classes later after your MCA, if you want to excel in data science, if you have taken up some course, they'll be talking about critical values. Then that time you'll come back and deliberate more on this kind of topics. Okay, so the critical value is determined by the confidence interval that we are considering. Thus, just as we could calculate the 95% confidence interval for true error to be, how we calculated this, we know, right? 0.30 sample error plus or minus critical value multiplied by square root of sample error into 1 minus sample error divided by n. That will give you 0.07. You calculate that. It is square root of 0.30 multiplied by 0.7 divided by 40. You will get 0.07. Okay. So that will give you the true error when you take 95% confidence interval. But when you take 68% confidence interval, then you have to change the critical value. This is the critical value, 1.0 is the critical value. See, when you take 68% confidence interval, what is the critical value given in the table? 1. So instead of instead of 1.96 for confidence interval 95, you are taking 1.0 for confidence interval 68. Thus, you will calculate the error value, true error value for the confidence interval 68%. Got it? Note, it makes intuitive sense, default sense, that 68% confidence interval is smaller than 95% confidence interval, because we have reduced the probability with which we demand that true error fall into the interval. Got it? Now, when I am saying there is 95% confidence interval, I'm claiming 95% confidence interval, I say that my machine learning model performs very well with unseen data. But when I claim that I have only 68% confidence, the confidence interval is only 68%. I'm saying that my machine learning model may not perform that well. It will predict well only for 68% of the time with unseen data. I can't guarantee about the other percentage on the other side. Means 32% of the time I can't guarantee whether it will make correct predictions or not. Here my confidence about the machine learning model is very, very low. Here my confidence about the machine learning model is very, very high. Now when I take my confidence interval as 99%, I say that my machine learning model is making correct predictions 99% of the time. And for mission critical applications like lifesaver systems, or in many applications where the accuracy is very, very critical, you have to take the confidence interval as 99% or sometimes 99.99% also. Got it? That good should be the accuracy of your machine learning model. You should have confidence about your machine learning model that 99.99% of the time my model will perform well with the unseen data also, so that its true error and the sample error which I tested both are the same. Okay, that is the importance of confidence interval. Did you understand clearly? Now, in the next coming session, we'll deliberate more on basics of sampling theory. Now, students, can you quickly answer these questions? What is Z? What is Z we have used in true error calculation? Z is a constant we have used in true error calculation, right? When you are calculating the true error, 1 second. What is the notation we are using? Yeah, true error with the hypothesis. We are taking it as sample error with the hypothesis plus or minus z multiplied by sample error into 1 minus sample error divided by n. Right? Now I am asking you, what is this z? Students, I want you to answer.
Constant, ma'am.
What is that z? I heard someone answering.
Constant.
Constant. What is that constant called as? It varies with the confidence interval. We know that. But what is that constant called as? It is called as critical value. Critical value associated with that confidence interval. For 95% it is 1.96. For 68% it is 1.0. Like that, the critical value varies with the confidence interval we are considering. Now, what is the confidence interval? Can anybody give an example for this confidence interval? Confidence interval is the probability with which you are claiming that your machine learning model will perform well with unseen data. It will make whatever error you have encountered with sample, same error it will make with true data also, unseen data also. It will not make any errors more than that. Okay, so when you are telling I have 95% confidence, my confidence interval is 95%, I'm indicating that my machine learning model will perform 95% of the time correctly with respect to unseen data. Okay, that is called as confidence interval. What is sample error? What is sample error? The error associated with the sample is called as sample error. Means among the sample data points you take, say 40 sample data points are taken and 5 data points are predicted wrong out of that, then your sample error will be 5 by 40. Okay, and what is the true error? When you take some unseen data and prediction errors are made with that unseen data, over the total number of labels predicted, that will be your true error. You take some new instances, unseen instances by the model. Now, among those instances, how many errors it has made over the total instances it has taken, that will be the true error. Got it? Any doubts in today's class, student? Students? You have any doubts in today's topic? Because
No, ma'am.
foundation, yeah, you should not have any doubt, otherwise later concepts will be difficult for you. Okay, then we'll end this class and meet in the next class.